So we are going to our next presentation, and that is hands-on practice. Classify the precancerous. The previous one was the BGG net or the sequential net. Now it is attention guided. So I think for the first semester students may be helpful in the machine learning uh, for this kind of hands-on or some practical example. So today with me, with this session, assisted or assistantship by Joydeep Roy, our one of the research scholar of our lab. So I think you will do some um, that is RaceNet, I think. Joydeep, RaceNet, na? So
Yes, sir.
yes, sir. So I think you can skip some of the same introductory parts. I think everyone know as the total thing is I think they have understood. So I think you should go the precise and those which parts are most important for the implementation of anything of this cell biology. So okay, and this kind of thing, how to uh, go your main curriculum or the main hands-on. So you can start, Joydeep.
Okay, sir.
Okay, stop. Going to stop the share. হ্যাঁ, বন্ধ করে দিছি।
Hello. Am I audible?
Yes, yes.
Yes, Jyoti.
Thank you, Mihal sir, for giving me this opportunity to present today's tutorial hands-on practice using the microscopic image to classify normal or abnormal precancerous cell with attention-guided combination neural network. So, good evening, everyone. So, as my outlines were like introduction to microscopic images, importance of microscopic image collection, types of microscopic image collection, data set overview, then methods of microscopic image classification, BGG16. Why should you use BGG16 and why should also be used ResNet architecture and the implementation. As our sir told that these parts were previously said or explained, so I'm telling very shortly about these things. So what is microscopic images? Like it is an image enable visualization of biological cell and tissues using different types of microscopes. In cancer research, microscope imaging is extremely important because it helps us identify early changes in the shape and the structure of the cell. So, skipping some slides, let me tell about the dataset overview. I will be using AGMC TU paper smear cytological image dataset, which is developed in AGMC Tripura University for automated cervical cancer detection through microscopic paper smear images. And it is considered to be as a binary class. Which includes 100 images, 50 normal and 50 abnormal, which makes it a balanced binary classification data set. Each image also comes with a pixel level marks, helping the model learn exactly where abnormal nucleus regions are located. Since the data set comes from the Tripura, It also takes the overview of our region, the northeast region, that how it works in our area. Overall, the dataset serves as a foundation for building and testing deep learning-based systems like BG16 or ResNet. Next, my dataset will be HALEV dataset, which is also a publicly available dataset categorized by seven types of seven types of different class. It is a multi-class dataset containing 917 cervical cell images. This class includes three normal types and four abnormal types. Three normal types are like superficial, intermediate, and columnar cell, and four abnormal types representing different stages of dysplasia and carcinoma. Because it has more than two categories, we use the dataset for multi-class classification, which allows the model to not only detect abnormal cells but also identify the specific stage of abnormality. All images in the dataset were labeled and verified by expert cytologists, ensuring high quality ground truth. Moving towards the next slide, uh, what are the types of microscopic image collection? As earlier we used to see that traditional methods were there for classification of the cells, microscopic cells images. Traditionally, researchers used machine learning techniques. In these methods, we first extract features manually, such as textures using LBP or HOG, means histogram oriented gradients, shape descriptors like the nuclear size or color features from the stained image. These features are then fed into classifiers like SVM or random forest to predict whether uh, the cell is normal or cancerous. However, the problem with the traditional method is that they depend heavily on handcrafted features. The accuracy depends on how well we choose these features, and they don't generalize well when the dataset changes. That's where deep learning comes in, like CNN and the other neural networks, which automatically learns useful features from the image themselves directly from the pixel data. Architecture like BG16, ResNet, and ResNet have been very successful in biomedical image analysis. The biggest advantage of deep learning is that it provides end-to-end learning, meaning the system learns to extract features and classify images simultaneously without manual intervention. This results in higher accuracy and better generation, especially for complex medical images. So there is a difference why we should use deep learning over traditional methods. So why we are focusing on deep learning methods like BG16 and ResNet instead of traditional machine learning methods? The main reason is feature learning. Traditional methods requires us to manually extract features from images like texture, color, or shape. This process is not only time consuming but it may also miss subtle patterns that are important for detecting cancer. In contrast, deep learning models, specifically CNNs, learns features automatically from the raw images. They can capture complex patterns, spatial relationships, and subtle changes in the cell structure, which are often invisible to handcrafted features. Moreover, CNNs provide end-to-end training, meaning the model itself learns both the features and the classifiers in the single pipeline. This reduces human bias and increases robustness to variations in staining, image quality, or noise. Finally, deep learning models scale well with large dataset, even small dataset also. For example, the HALEV or the AGMCTU dataset. There is a short difference of BG16 versus ResNet, as my earlier mate has explained about the BG16. It is a sequential CNN architecture which carries 16 layers. It stacks 3 into 3 convolution layers to learn features hierarchically. While it works reasonably well, it has a huge number of parameters, around 138 million, and can overfit a smaller complex dataset. ResNet, on the other hand, introduced residual learning using skip connection, which will be discussed in the further slides. These connections allowed the network to bypass layers and help solve the vanishing gradient problem, which is also be discussed in the next slide. why vanishing gradient is a problem in the deep neural network, enabling much deeper networks to train effectively. Despite having 50 layers, ResNet 50 is a more parameter efficient than BGG16 and achieves better generalization on complex or multi-class dataset. In short, BGG16 is simpler and good for small dataset, but ResNet is perfect for medical image analysis. So, what are the challenges with deep neural network? So, let's see why we use ResNet when we train a deep neural network. We update. Actually, these are the problems faced during a deep neural network. In the uh, while a input image has been trained in the artificial neural network or deep neural network, there it happens back propagation. But deep network face vanishing gradient issues while using the chain rule during the back propagation, because in the when the input image is shared over this layer, that in the hidden layer, and then the output comes and does not match with the predicted output, then hence it goes back to the hidden layer. While going back to the hidden layer, it faces the gradient issues, because at that time uh, chain rule is observed. So so as we go backward through the layers, each step involves a multiplication of small derivative values with multiple layers. These products become extremely small when you reach in the suppose there are 3, 4 to 5 steps over this layer, and up to coming to this layer, the value becomes very small, and when they reach the earlier layers, the gradient almost vanishes. So this is a effective problem in the deep neural network. Earlier layers stops learning effectively, leads to slow or failed training in deep models. In that case, ResNet helps to fix this shortcut connection. So this is called the vanishing gradient problem. The network stops learning properly because the early layers can't get enough signal to update their weights. To overcome this, ResNet helps because it introduces skip or residual connection, which allows the gradient to bypass some layers and flow directly backward. The simple idea ensures the model can be trained much deeper, like ResNet 50 or ResNet 101. Let me explain about this. This is a normal network layer which a input image is converted is going to a convolutional layer, and then performing the batch normalization, the pooling, and the ReLU and the pooling layer, then again to the convolutional layer. It is a normal network of deep neural network. But what happens in the ResNet? It follows uh, it follows the network like a residual mapping. From X, if we take X as the input, and then it comes to a convolution layer, performs batch normalization, ReLU, pooling, again to the convolution layer. But in this case, they are happening three direct layers. But while using ResNet, it skips some layers and directly goes to the output layer. We consider FX as the output layer. So the final output becomes hx, means the x equals to fx plus x, because the residual mapping is fx equals to hx minus x. The learning should be like this, that the x means which carries some information is directly going to that addition symbol that carries information and resolves the gradient problem. This shortcut allows gradient to flow directly to the earlier layers during backpropagation. This prevents vanishing gradients, enabling the training of the deep neural networks. These cliff connections means the gradient does not have to flow through every intermediate layer. It can directly reach layers, so even if some gradient becomes small, the shortcut helps to preserve them. So it is the residual network is denoted as hx equals to fx plus x. Moving towards the next slide about the ResNet architecture. If we consider an input image of 224 into 224 of three channels and into three channels, in the first layer of ResNet, the input image passes through 7 into 7 convolution layer with 64 filters and a stride of 2 and a padding of 3. The ResNet 50 the structure is like this, that it first the initial layers comes with the 7 into 7 convolution filter, then max pool, then 1 into 1 convolution layer and 3 into 3 convolution layer and 1 into 1 convolution layer with 256 filters will be continued three times, that is 9 times. Then again with this into 12 times, and again the same type of convolution layer of 4 will be converted into 6 times, so it comes into 18, and then again in 3 times, which comes in 3 into 3, that means 9. And at last there will be a average pooling layer with fully connected with 100 neurons. This is actually the 50 layers of ResNet. Now let me explain how it uh, solves the each layer, because in the earlier slides or earlier session you have seen how convolution works. Now I'll be showing that how ResNet works in this convolution with this formula, that n plus 2p minus f by s plus 1. There is nothing, just normal convolutions. See here, if you take a input image, here converts it to the initial layer, that is 7 into 7 convolution with 64 filters and a stride of 2. Here is the first layer explanation. See, the input size n is 224. The filter size is 7 into 7, which type 2, the padding is 3, and the feature map or the number of filter is 64. We are not explaining going to the number of filters, because the about the filter thing in the earlier session it has been explained. Output size equals to how much will be the output size, depending on this formula. Input size plus 2 into padding minus filter size divided by the stride plus 1, it will decrease the uh, output size will be decreased in every each layer. See, when it comes 112.5 into 112.5, since we take the convolution layers as floor values, the output size will be 112 into 112 into 64. This is just an example. The input size will be can be anything. It can be 116. Here we have taken the input size as 224 into 224 into 3 channels RGB. In the next, sorry, here is some problem. Okay, in the next here there is happening that max pooling, which again it is another layer which converts the will take the input images, that output of that layer, 112 into 112 into 64. This will be the input for the next layer, and hence again the same problem will be solved, and hence it will come as 64 into 64 into 64 56 into 56 into 64. After that the main convolution layers will be having. So these skip connections, what is this skip connection and why this skip connection one is in the dotted lines? These three skip connections are known as the identity blocks. There are two blocks in ResNet. One is identity block another is convolutional block. In identity block, here we explain that when we when the input size and the output size is similar, it skips the connection and directly adds input x to the output of fx. That is x equals to fx. Our main motive is to that after the input size of our gets over the output size, it becomes 0, and it should follow this rule x equals to fx. So no convolution layer is shortcut in this part, helps preserve original features and gradient flow. Here the sizes get similar. Is the output layer, the output sorry input layer of this part is equals to the output layer of this part. Again for this convolution, 1 into 1 cross 1 convolution and 64 filters. For this skip connection also same thing is happening. The input layer equals to the output layer. When it comes to the convolution block, what happens here? The skip connection needs the input size of the is not equals to the output size. Here is the problem over there. See, whenever there is an input size which is not equal to the output size, at that time you use the convolution block. And how to match with the output size? For this purpose, there are two options. We can perform 1 into 1 convolution, or we can do padding with the input volume, or you can say the input layer. But we will perform here 1 into 1 convolution to get the same output as the input size. Same again, filter size will be 1 into 1, because we will be doing 1 into 1 convolution over here to match the dimension. Then the same like the output size will be doing, and it came 28 into 28, and the filter size has been increased to 128. So it became same. The output layer, the input layer to the output layer got into the same size by adding one convolution layer over the skip connection during the convolution block. This is the main purpose of giving this skip connection into dotted lines. Again, perform the identity block, 3 identity blocks, again one convolution block there. Then again 1, 2, 3, 4, 5, 6. Sorry, 5 identity blocks, and one convolution block, and then 2 identity blocks. And here is the average polling, which strike 2 is okay. One more thing over in the over here, that during the convolution block you can see the first slide 1 into 1 convolution, and 128 size is the filter size, and we are taking as strike 2 to just match the other to just match the other input size, such that it reduces its input output value to the next input value. For this purpose, in every convolution block, the first layer is having strike 2. Now let's go to the code implementation of the residual blocks. As we know, we will be doing this code over Spider, or we can use even Colab or Kaggle for the purpose of GPU. So I will be using TensorFlow Keras module for implementing this code, which is from the basic, from the scratch actually, the residual blocks and the convolution blocks. So at first, what we'll be doing here, we'll be inputting the libraries. What is like the TensorFlow, which is a code deep learning framework, layers, modules, input, or for the model purpose, image data generator for the image loading, and the image augmentation for the data set we will be using. Next, we will be using matplotlib and numpy for the visualization and the numerical operations, sklearn for metrics, for evolution metrics, and at last we will be using the Adam optimizer for the training purpose. So here is the main residual block definition. Uh, Defines a convolutional block which are used when the input and the output definition, dimensions include three convolution layers, 1 into 1, 3 into 3, as you have seen in the figure also, 1 into 1 convolution layer, 3 into 3 convolution layer, and 1 into 1 convolution layer. The convolution layer is also called as residual block, used when the input and output dimension includes the base normalization, the ReLU activation, the normal functions of the convolution over here will be doing. At next, we'll be using the identity block where the input size and the output size are the same concept of residual learning, no dimension matching needed. Shortcut directly connects input to output. As you can see, the layers convolution F1, filter 1, then the filter 2, then the filter 3 base normalization, and the activation is used over here is ReLU. Again, building the ResNet model. Now the ResNet model has been building because we have seen the convolution block, even the identity block. Now we'll be calling the ResNet 50 model. How will we call? Here we use the input shape 116 to 116 to 3. Okay, but I have shown the input channel. The example was about. Sorry. The example was with the input size of 224. But here we have taken the images of the input shape of 160 into 160 and 3 channels. Number of class 7 because the Halep dataset contains 7 classes. To initial convolution and the pooling of the low-level features, post stages of residual blocks ends with the global average pooling and the softmax layer. Here, all the layers of the residual block and the convolution block are being called over here because we have used definition over here. See, residual block definition, and for the same identity block we have used definition, and here it is the calling of the definitions. Then we use the data set processing, which augments the data to rescale the change of shear range, arrange, and shift range, and the horizontal flip. The train data and the for and giving the location of the training data and the testing data over here. Here we used the model to epoch of 200 with the optimizer of Adam optimizer of to compile it with the learning rate of 0.001 with the loss of categorical entropy cross entropy for classifying the 7 different classes of the cells which can be abnormal or normal. Further, it will be distinguished in the test class that it is normal or abnormal. Here is the evaluation of the results. After training, I evaluate the model on unseen test data, but here we have given the training and validation accuracy. Here is the validation accuracy which came 0.7 and the validation loss of 0.6 because we have very limited data set and I have been training this model in a scratch, so the accuracy is not so well. If I take pre-trained model like ImageNet, uh, then it might go into the good classification. Now introducing the attention mechanisms. I'll be showing this code over Spider also after completing this whole slide. Let me complete it. Moving towards the next slide, which is about the introduction to attention mechanisms. In traditional CNNs, all feature map regions are treated equally. The model does not know which areas of an image are more important. But using attention mechanism solves this by guiding the network to focus on informative regions, similar to how humans pay attention to relevant parts of a scene. Like suppose a human can also pay attention that okay, this thing is important for me. I need to put attention over here. So this is how attention module works in a ResNet model. In a ResNet model. These are several types of attention like spatial, channel, and self-attention, and each helps the model prioritize using useful information for better feature learning. Attention-guided CNNs are especially used in medical imaging where critical lesions might be very small and subtle. See, there are two main types, channel attention and spatial attention. Channel attention focuses on what is important, and spatial attention focuses on where it is important. Next, we are going to the next slide of attention guided CNN architecture, which incorporates attention blocks with standard CNN pipelines. During a model, if you are doing a CNN model, you are training a CNN model, in which part you will give the attention, in which part you will give the attention, it is a very critical stage to put attention in a effective manner. To use the attention module in an effective manner, it is an important part. Each attention block refines feature maps through adaptive weighting. This leads to faster means attention acts like filters, emphasizing the most relevant feature maps and suppressing unimportant ones. This leads to faster convergence, higher interpretability, and better classification accuracy. We use attention modules in deep architectures like ResNet to make the model focus more effectively during the feature extraction. Here is an example of we will be using CBAM attention module for the ResNet, and here is an example of CBAM architecture, how it works. It takes the input feature, then it does max pooling and average pooling along with the shared multi-layer uh, perception, and again doing the max pooling and the average pooling, which gives the channel attention. After that, this is the special attention module where the convolution layers are connected to the channel refined feature and the spatial attention. Here we have given a formula how the CBAM works. That is f dash equals to ms into mc, which is again within bracket with f, and last the multiplication of f. MC is the channel attention mask, and MS is the spatial attention mask, and F is the filter, and F dash will be the uh, output of this channel, convolution block attention module. It is a lightweight plug and play module that can be added to any CNN architecture without increasing competition too much. How does it works? Okay, how does it work? The first, the channel attention mechanism computes both average pooling, which I said over here in the figure, uh, average pooling and max pooling along spatial dimensions. The spool features are passed through the shared MLPs and combined using sigmoid activation to generate channel attention. The input feature map is multiplied by this weight to enhance the importance of channels. Next, spatial attention operates. It takes average and max pooling along the channel axis, concatenates them, and passes them through a 7 by 7 convolution to produce spatial attention map. This map tells the model where to emphasize. Now I'll be integrating CBAM with the ResNet. So CBAM is inserted after residual addition and ReLU activation. The implementation part of this layer is written over here, that the layers of add and the activation and the CBAM block. I'll be showing this in a sketch which is used in both identity and convolution blocks, enhanced ResNet with attention guided feature line. But let me show you the code of using this part. Is this visible? Can anyone tell if it is visible? Okay, thank you. See, here the definition of the C1 block is present. How it works, let me tell you. Same, the thing which you have seen in the figure, this only part. CBOM features shape, the shapes are taken. Shared dense layer activation is normal. ReLU kernel initializer, the normal zeros, and the again the bias initializer zeros. The average pooling is done over here about 4 times with the layers and the shared dense layers. Again the max pooling, then the channel attention is uh, added over here. This block first calculates the average and the max pooling across the channels to create a channel attention map. Then it does the same specially to produce the special attention map. Both are multiplied with the input feature to refine it. This block is defined over this C1 block, which applies channel and special attention sequentially. And this part is called over here, like in the convolution block, see x is to C1 block. Again in the identity block, x is to C1 block. And over the skip connection, it is present. The part where the convolution is added, in that part I have shown you that in convolution block we have to do one into one convolution. At that part we can also do the C1 block for uh, similarizing the input size and the output size. And here is the overall network of the RESTnet. So let me show you how it works. Let me run for this for one epoch. Already here one confusion matrix is there, but since we have used only one epoch, it will not show anything. It needs to be trained more gradually, like 200 or 300, because the whole model is from the scratch. We didn't use any pre-trained model over here. Well, I can show you the main ResNet model summary. Sorry. Sorry, the model summary is not present over here. Okay. Okay, let me tell you the network architecture of using the CBOM. Convolution one, you see over here, one CBOM is added again in the convolution 2x. Let me go to the presentation again. This part. See, in each and every layers, the CBOM has been added in all the blocks, such that you can define the RESTnet and give the output in a good manner. Okay, here is the implementation of that CBOM RESTnet. This is the normal CBOM trained on the Haleb dataset. Okay, we trained our dataset. We actually used Haleb dataset, even the AGMC2 dataset for training this purpose. There is the main code for the ResNet and the CBOM. Same validation. CBOM block, which I told you about the spatial and the channel attention. Here is the model summary of using. See, here actually given 224 shape, and then again the convolution is reduced. The filter size is the input size is matching with the another. If doesn't match, we will be using convolution block. So, this huge model summary. The trainable parameters are like this because we used CBOM. The trainable parameters just increased. Here is the validation accuracy over 80% and the loss is about 50%. So this is the accuracy and the loss. So from this we can tell that we can conclude that microscopic image collection is crucial for early cancer diagnosis and screening. Deep learning models like ResNet 50 outperform traditional methods by aligning features. Integrating CBOM enhances the model's focus, input cellular regions, improving accuracy and interpretability. The proposed ResNet 50 plus CBOM model demonstrates better performance on cervical cancer datasets such as HMCTU and HER. So here is the concluding statement, and thank you. If anyone has any question, kindly you can ask.
Joydeep, also tell them what is the difference between the sequential and attention based to them.
Okay. Okay, sir. This is a very good question actually. Let me show you here. In sequential CNN, the BG16 or layer was about a full sequential, like the convolution block was reducing one after the another. But if you using attention network or using skip connection, the layer get the input size also get the information to the output size. The input the here we can see if we take a input from here, we can get the information directly. We can get the information over here directly over here. Normally, a CNN architecture processes sequential layer by convolution, pooling, and layering. But in an attention-based CNN, spatial channel or self-attention is included in the skip connection, or we can say wherever we can want in the CNN to extract the features of that module. Even we can extract multiple features. Sometimes we get it get decreased during the CNN layers, normal sequential CNN layers. The goal is to dynamically assign higher weights to get the most information from the pixel channels of the regions. So am I clear, sir?
Yes, and any question? I think Ronit, Devojit, Devojit,
Yes, sir.
I think I am giving to you the some of the responsibility. Please talk with our first semester students, and tomorrow we will interact because whenever in future they will work in USA and other country. So I think they will be helpful if they talk with Professor Nath. Okay.
Okay.
And secondly, if any kind of question, please ask. Yeah, Devojit.
Uh,
Okay. So that is demonstrated well, uh, Joydeep. And once again, I am giving you that to credit that you have beautifully completed all the, that is the conceptual part, and their convolution layer, pooling and other things. So thank you again, and we will meet tomorrow at 10 o'clock. And tomorrow is the last day, so please cooperate with us. I am requesting all of the participants, please. Okay.
Thank you, sir.
So thank you to all, and the completion of this session. So Pooja, please formally end. Please end this session.
Thank you so much, sir, and thank you, Joydeep, for nice presentation. And today there is a very important note for tomorrow's session, as we know that tomorrow is our last session for lectures and tutorials. Other than this, we have to be in Zoom's link for last two session uh, uh, for exam session and the valedictory session. So we will be there in Zoom link for last two session also. That is the reminder for everyone. And we will have an examination called quiz. And another thing, we will send you a Google form via your mail address. So you will send back to us the scan copy of the Google form by filled up by yourself. That's it. Thank you so much, everyone, for your kind attention, and we will see you soon tomorrow at 10 a.m. Thank you so much.
So Pooja, if anything is pending, please explain them about the, that is the quiz or the multiple. Anything that is they will prepare themselves.
Uh, every question in the examination or the quiz session will be from the slides that was in the tutorial 1, tutorial 2, and lecture 1, lecture 2, likewise. So everyone, please go to YouTube session if any kind of reference you want. There will be very simple question about biological things and the machine learning things also. And if anyone any queries, please contact me or Joydeep for further queries. Or you can ask now also if anyone any queries regarding the exams.
So many thanks. So don't worry about this. That is the quiz or anything. Everything will be. We will help to all of you. Don't worry. It is a very simple thing. Just we will discuss. Okay. So thank you to all, and we are ending this session. Pooja, proceed.
Thank you so much, sir. Please, everyone, leave this session. We will meet tomorrow.